In this lesson, we're going to start looking at testing the difference between two population means or two population proportions. And we do this when we want to compare two population means or two population proportions. Now, the next few methods that I'm going to show you in section 1, 2, and 3, these are based on independent samples. So let's first talk about independent samples. We talked about it previously in probability, so we're going to review that concept of independent once again. So if we have two samples that are independent, what that means is there is no relationship between the values of the two distributions. So if we are testing the difference between two population means or two population proportions and they're independent, that's what we're going to cover in the next few sections. So the first situation that we're going to cover is if we're looking at comparing two population means and we don't know the standard deviation for either one of those populations. And we're going to walk through how to run a hypothesis test in this case. Now, the steps of a hypothesis test is not going to change because we have two samples. The only thing that's going to change is how we set it up in the beginning. But the concept of each step is going to remain the same. In step 1, we're going to set up our hypothesis. In step 2, we're going to determine the type of test, find our test statistic. Then in the next step, we're going to do our rejection region, then our p-value method, and then the last step is going to be conclusion, just like we have been doing so far. The only difference is in how we set it up. Now, to justify using two-sample t-test on our calculator, this is what we need to make sure happens. We need to know x1 bar and x2 bar. So x1 bar will be the sample mean from the first population, and x2 bar will be the sample mean that comes from the second population. We also need the sample standard deviation from each sample that comes from the corresponding populations. The next thing we need is that the two populations have a normal distribution or the sample size for each sample has to be greater than or equal to 30. So these are the things that we need. And then 3 is an or statement. We need to make sure that the two populations are normal or approximately normal, or we need a big enough sample size. When we set up our hypothesis in step 1, we're going to have 3 possibilities. If it's left-tailed, then we have the situation where we're looking at the left tail, our null hypothesis is going to be set up so that we would say mu1 minus mu2 is equal to 0. And so mu1 is the population mean from the first population, and mu2 would be the population mean from the second population. Now, when we set up the alternative hypothesis, if it's left-tailed, that means mu1 minus mu2 is going to be less than 0. And another way to state that is that mu1 is less than mu2. And we know this because if the difference between two numbers is less than 0, meaning negative, then the second number has to be bigger and the first number has to be smaller in order to get a negative number. Okay, if it's right-tailed, then we're going to have this situation where we're looking at our right tail. Our null hypothesis is still going to be set up that mu1 minus mu2 is equal to 0. And then the alternative hypothesis is going to be mu1 minus mu2 is greater than 0. And another way to say that would be that mu1 is greater than mu2. Because if I take the subtraction of two numbers and it's positive, then mu1 has to be bigger. Okay, and then the last possibility for step 1, when we set up our hypothesis, if we have two-tailed, then we're not looking to see if the difference is greater than or less than 0. We're looking to see if there's any difference. So we're going to write it like this. The null hypothesis is going to be mu1 minus mu2 is equal to 0. And the alternative hypothesis is going to be that mu1 minus mu2 does not equal 0. Another way to say that is that mu1 does not equal mu2. In step 2, if we have the justification, then we would use two-sample t-test to get our p-value and our test statistic. And for those of you who like to use the formula to calculate the test statistic, it would be where I take my x1 bar minus my x2 bar, and then I divide by the square root of the sample standard deviation from the first sample divided by the first sample size plus the standard deviation from the second sample squared over the second sample size. And I add those together and it's all under the square root together in the denominator. If you are going to use this to calculate it by hand, make sure you put parentheses around the numerator and the denominator to make sure that the calculator knows or understands the order of operations correctly. The first example says, 2 competing headache remedies claim to give a fast-acting relief. An experiment was performed to compare the mean length of time required for bodily absorption of brand A and brand B headache remedies. 12 people were randomly selected and given an oral dosage of brand A, and another 12 were randomly selected and given an equal dosage of brand B. The lengths of time in minutes for the drugs to reach a specified level in the blood was recorded. The mean, standard deviations, and sizes of the 2 samples follow. So here's all the information that was collected from each sample, from brand 1 and from brand 2. Past experience with drug composition of the 2 remedies permits researchers to assume that both distributions are approximately normal. So that's good. If that didn't say it in there, then we would be concerned because our sample size wouldn't be big enough. Remember, our justification is the sample sizes need to both be greater than or equal to 30, or the two populations need to be approximately normal for this to work. Okay, let's use a 5% level of significance to test this claim that there is no difference between the two brains in the mean time required for bodily absorption. So here's some more key information here. We're checking to see if there's a difference between the two brains. It doesn't say if we're checking that one's greater than the other, one's less than the other. We're just looking to see if there's a difference. Okay, so in step 1, we need to set up our hypothesis. Since we're testing means, this is going to be mu1 minus mu2 is equal to 0. The alternative hypothesis, since we're checking to see if there's a difference, we're just going to state that mu1 minus mu2 does not equal to 0 for the alternative hypothesis. And our level of significance is 0.05. Now, because we do not know the population standard deviation for either of them, and we know that we have justification because it says the populations are approximately normal, we can use the two-sample t-test. So I'm going to go onto my calculator. Unless you want to try using the formula, that's totally fine. I'm going to go onto the calculator, and I'm going to go and find my function, two-sample t-test, under the stat and the test option. And then I'm going to find, after I put in all of my information, that the test statistic is 0.875 and the p-value is 0.3915. Now, in order to put all that information in, we also need to know that because we're looking for any difference at all, this is a two-tailed test. Okay, so all of that information we get from our calculator, unless you want to try doing it by hand. In step 3, we're going to do the rejection region method. Now, because this is two-tailed, I'm looking at both wings. And because we're doing a t-test, in order to find those critical values, I'm going to do inverse t, not inverse norm. We're using the t distribution here, so we're going to do inverse t. When I do inverse t, I'm going to find that my critical values, my cutoff points for that rejection region, is going to be 2.2, and then by symmetry, negative 2.2. Then I'm going to look at my test statistic, and I'm going to see where that falls on my graph. If I look, here's 0 again, as always, in the center. My test statistic is 0.875. 0.875 falls between 0 and 2.2. So it's going to fall in between here, which tells me it's not in the rejection region, right? If it fell in that red area, that would be our rejection region. So that tells me to say do not reject the null hypothesis. For step 4, we're going to use the p-value method. We got that our p-value was 0.3915, and that's definitely bigger than our 0.05 for our alpha. And whenever our p-value is greater than our alpha, we say, do not reject the null hypothesis. So these two match up. Okay, the last step is we're going to write our conclusion. We're going to say at the 0.05 level of significance, there is not enough evidence to conclude that there is a difference for the bodily absorption. Now, I forgot to mention up here, just a quick reminder in case you forget, when we did inverse T, because this is two-tailed, the alpha level, which is 0.05, has to be split between the two wings. I forgot to mention that. So remember, this is going to be 0.025 for that area, and this area is going to be 0.025 under the graph in that red area, because we took the 5% level of significance and we split it into two 2.5% areas. So just a quick refresher on that, because I feel like I went through that pretty quickly. Okay, second and last example. Suppose the experiment to measure the times and minutes for the headache remedies to enter the bloodstream yielded sample means, sample standard deviations, and sample sizes as follows. So here's the information. Brand B claims to be faster. Is the claim justified at the 5% level of significance? This is actually a continuation of the previous example. These two populations are going to be normally distributed, and we need that because these sample sizes are not big enough. Remember, if we don't know that it's normally distributed, our sample sizes need to be 30 or bigger. And we don't have that here. But we know from the information that's given in the first part in the previous example, it does tell us that this information from brand A and brand B, these have normal distributions. So we can justify using a t-test here. But in this example here, we're looking to see if it enters the bloodstream faster. So in step 1, we set up our null hypothesis. We have mu1 minus mu2 is equal to 0. The alternative hypothesis, since we're looking to see if brand B, which comes from the second population, is faster, that means it's going to have a lower time, which means mu1 minus mu2 is going to be greater than 0. Another way to look at that, if you're trying to wrap your head around it, if brand B, which would be the mean time, mu2, is faster, that means it's going to have less time, so mu2 is going to be less than mu1. So that's the other way you can write it if it's easier for you to understand it that way. The level of significance is 0.05 again. It's 5%, written as a decimal is 0.05. Now in step 2, we already know that we can justify using a 2-sample t-test. Because we're checking to see if mu1 minus mu2 is greater than 0, that's going to be a right tail test. Now I'm going to go into the calculator to the 2-sample t-test option, and I'm going to put in all this information that's given to me up here in the problem. When I do that, I'm going to get a test statistic that is 2.437. And we're going to get a p-value that is 0.0132. So now we're going to use this information to create a rejection region. It's a right-tailed test, so I'm going to be looking at the right tail. I want to find that cutoff point, so I need to find my t-critical, and I'm using t-critical because this is a t-test. So to find that critical value, I'm going to use inverse t, And I'm going to find that my T critical is going to be 1.89. That's going to be my cutoff point. Now, when I check that against my test statistic, 2.437 is to the right of 1.89. That means that the test statistic falls in that rejection region. So we're going to state for part 3, reject the null hypothesis. In step 4, we're going to use the p-value method. Now, the p-value that we got on the calculator, we got 0.0132. And we want to check that against our alpha level. This is certainly smaller than 0.05, which is our alpha. And whenever our p-value is less than our alpha, we say reject the null hypothesis. So all we have to do now is write our conclusion. So we can say at the 0.05 level of significance, there is enough evidence to suggest that brand B is absorbed faster in the bloodstream. So you can see the steps in our hypothesis test is staying the same with the 2 samples. The only difference is how we set up our null and alternative hypothesis, and then the calculator function that we use, or the formula. If you're using the formulas, the formula for the test statistic is changed. But other than that, the concept for each step is going to remain the same.